What happened in the very beginning? Before us, before planets or the sun? What happened in that very first nanosecond of time, the instant the universe began, that allowed nothing to become everything? Impossible to know until now.
100 meters below us is the largest science experiment of the world.
After decades of preparation, one gigantic particle accelerator is on the verge of changing everything we know about the universe. The greatest scientists in the world are looking to this huge machine to recreate the conditions 13.7 billion years ago, in the first moment after the Big Bang. You are about to take a phenomenal exploration to see what may be discovered when a controversial $8 billion machine turns on in 2008. Will it reveal extra dimensions of the universe? Will it explain what dark matter is? Will it reveal a kind of universal supersymmetry? Or explain why we even exist at all by unveiling the God particle? Perhaps, but one thing is certain.
What we discover at the LHC may be the next Big Bang in physics.
This is the next Big Bang.
Hi, I'm David Kaplan. I'm a particle physicist, and over the next hour, I'm going to try to explain why we're building the largest science experiment in the history of the planet. It's called the LHC. It's a tunnel 16.5 miles around and more than a football field underground. It's filled with the most amazing technology in existence. LHC stands for Large Hadron Collider, meaning it's very big and it accelerates and collides hadrons, which are particles. We do this to see deep into the makeup of everything. Trillions of protons will travel in opposite directions around the ring, accelerated to the speed of light, until the beams converge and the particles collide at 4 separate experiments.
And it's here, at these 4 points, from these powerful particle collisions, that David and other physicists will get a clear picture of the universe's beginning.
Imagine this line is the history of the universe. This direction is time, and this direction is temperature, us. Hello. The beginning, I have the Big Bang. Now, we live here because we can't live here earlier in the universe because it's too hot. This is the time that stars formed. If I go before that, I get the time that atoms formed. This is the time when the temperature of the universe is the same as the temperature inside the sun. This is the time where the nucleus of the atom is formed. And back here is the time when everything is one big quark plasma. Before this, it's really hot. Particles are hitting each other really fast, and we have no idea what's happening. The only way to find out what this is to build a collider, smash particles together at that temperature, and then see what we see. The LHC's massive underground footprint is located in France and Switzerland. Particle beams will literally come from opposite sides of the border in order to collide. Really, really hard.
Particle physics is the study and the search for what things are made of. What are the fundamental particles out of which everything is made?
Particles are everywhere. They make up everything. The mountains in the sky, trees, cows, grass, birds, soil, people, all particles. What makes any one object appear different from any other is simply the way the particles are combined. But if you look deep inside anything, say water, you find molecules made of atoms. Atoms are made of particles like protons and neutrons, which are made of even smaller particles called quarks. In the early universe, there were no atoms. Quarks and other particles were just smashing into each other at super high energies.
In order to reproduce that state, the LHC must collide protons at the speed of light.
Sometimes we make particles that are much, much more massive than the incoming particles. That's basically because we're transferring the energy of those particles into mass.
You can create particles at maybe don't occur naturally. At least they don't occur naturally now, but they occurred naturally very early on in the history of the universe.
The more powerful the collisions, the closer we get to the temperature of the Big Bang. To comprehend that, you have to understand what temperature means.
What is temperature for a physicist?
It's just particles moving. So when your stove is hot, it means all the particles in your stove are moving really fast.
And if you make them move faster, it gets hotter.
Of course, temperature has to do with energy.
When the universe was really hot, well, all the particles of the entire universe were moving very fast and smashing into each other.
When you hit something with a hammer, part of the energy, part of the kinetic energy of the hammer goes into hitting this stuff up. At high temperature, you have primordial soup of particles, and they continuously collide.
When you collide the particles, you're creating huge temperatures, thousands, if not millions of times the temperature of the core of the sun.
So, by colliding particles in huge numbers at the speed of light, we reach near Big Bang energies.
And enormous energy there is equivalent to this hot temperature at the beginning times of the universe.
Now, before particles can collide at the LHC, they have to run through a series of smaller accelerators.
So what you do first, you take the proton and you give him a kick.
The proton bunches are sent through 4 separate machines, using more and more powerful magnets to increase their speed.
Then you inject it into the LHC, a big machine, and then accelerate it to its top energy.
Accelerating not just one, but trillions of protons to the speed of light.
To be precise, they travel at the speed of light minus 10 kilometers per hour.
Really fast. It would take you 15 minutes or so to drive the length of the ring, while a proton in the LHC does that trip 11,000 times in a second. Those protons are kept on course by over 9,000 superconducting magnets.
1,232 of them are called these big dipole magnets, they're called, and they're what make the beam go around in a circle. There are 400 quadrupole magnets. They work like lenses. They focus the beam, and there are all kinds of other smaller magnets that just provide small corrections to the beam orbits. Most of the way around the LHC, the beams are in separate beam pipes traveling parallel, one going this way, one going that way.
And right before they get to the experiment, the beam pipes converge into one tube.
And then they collide.
Per second, there will be 40 million collisions happening.
You've got one packet coming this way, one coming that way. They collide 40 million times a second. But there's an awful lot of particles inside these packets, 100 billion in each of them. And when you do the sums, that means that you're getting up to 600 million individual proton-proton collisions a second inside the particle detectors.
Thus, replicating the conditions of our universe the instant it began.
You have to build a machine that big to get energy enough to mimic what was happening when the universe was a tiny fraction of a second old.
Humans have always had the curiosity to ponder the universe and find the makeup of things. Around the 5th century BC, Democritus, a Greek philosopher, uttered an amazing statement for his time.
The atom is the smallest indivisible unit.
That was a brilliant construct of the mind, you know, that things be made out of tiny little elements like that.
There is nothing but atoms and the void. Can you imagine having a theory, being deeply committed to it, and knowing you'll never be able to prove it in your lifetime?
Still, Democritus could imagine the atom. And now, we've already managed to look well within that tiny atom and its particles, allowing science to develop a clear picture of our universe 3 microseconds after it began. 3 microseconds. There are about 100,000 microseconds in a single blink of an eye. So since that picture is clear, what did the Big Bang itself actually look like?
If I was sitting there watching the Big Bang,
Would you have heard the Big Bang?
it's very difficult to imagine someone sitting there while space is exploding, because where is the guy sitting? The problem is the Big Bang is not an explosion in space. It's the explosion of space.
You can visualize it sort of maybe as a balloon, if you will.
But anyway, let's say you could.
So you got things moving back and forth inside this balloon. It's getting very hot. And all of a sudden, you take a pin and you pop that helium balloon.
Let there be light.
Everything that is space is completely bathed in high-temperature radiation, bursting with light. Very quickly, as the explosion dissipates, temperatures lower, particles start to bond and acquire mass, and the universe as we know it begins to form. Even understanding that much, scientists will use the LHC to learn what happened even earlier.
We want to roll the tape back and look at that first nanosecond.
1/10 of a billions of seconds after the Big Bang.
The very first nanosecond in time. That's 3,000 times earlier than we already know. What strange truths might that reveal?
Weird things can happen at the atomic level. Weird things can happen at the atomic level. Things can be roughly in two places at once.
There is a chance that anything can happen at any time.
Quantum mechanics says there's nothing solid.
They say there's a chance that this ball could fall through this chair.
They're not what we experience in everyday life.
Anything can happen once, so you have to do it a lot of times. You put the ball in the chair 100 trillion times, and then it fell through 10 times.
They're a probability function.
You could have some better sense of the probability than if it fell through once randomly.
Yes, there is a chance of anything happening at any time, but reality is a function of probability.
In the same way, there's probability for really strange things happening at the LHC. For example, you could produce a black hole.
Well, if the LHC produces black holes, I'll tell you, physicists would be incredibly excited.
It's unlikely, but there is a chance it could happen.
A black hole. Wouldn't that be dangerous? Could it swallow up the Earth?
A black hole produced at the LHC couldn't possibly swallow up the Earth. It would be the size of a proton. Smaller.
However,
there is a good chance that the LHC will help us to understand which is dark matter.
For the very first time in history, the LHC will likely produce signs of this nearly inobservable dark matter, which makes up the majority of the universe's mass.
Dark matter is different than a black hole.
Until the LHC turns on, dark matter will have remained completely elusive to us, though we've known it's there.
What is dark matter?
It's not atoms. It's the other stuff. Particles we've only speculated about, until now.
And we don't know what is made of.
it will be gorgeous that we are going to produce the particle which constitute 25% of the universe.
We call it dark matter.
It has absolutely nothing to do with the dark side.
Look up at the stars. All those bright things are a very small fraction of what is actually out there. The rest is mostly this invisible stuff, unrelated to the particles that we recognize. We call it dark matter. And right now, dark matter is passing through you at over 100,000 miles an hour.
What we hope to produce at the LHC is the particle connected with that dark matter.
That would move our understanding of the universe from 4% to 30% overnight, which is a pretty good jump to take in one go.
Darth Vader is still safe.
The road to understanding dark matter first required really understanding what matter is.
And that process couldn't have begun without something we now take for granted, called experimentation, a method brought to science by a man with a telescope.
Galileo Galilei was one of the first modern scientists.
He drops a penny and a big 50-pound weight. They fall the same speed.
Galileo modernized the telescope, looked into the stars to see what was actually out there.
He measures to see how the world actually is made, you see. That's a different experimental method which we do today.
And he brought the theory of atoms back.
Though Galileo was on the right track, what he didn't know is that atoms and everything else are made of particles. More particles than he could have ever fathomed.
The first glimpse of these particles within the atomic structure happened in the late 19th century, when Ernest Rutherford discovered there was something inside there. He called it the nucleus. That's when particle physics truly began.
Historically, the first important experiment of this sort would be by Rutherford, turn of the century.
This thingy is reproducing exactly what Rutherford did 100 years ago.
And he did an experiment where he took the most energetic particles of the day.
The radioactive source is spitting out what's called alpha particles. So, for example, if I turn this thing so that the source is directly facing the detector, then I get lots of counts. If I turned it this way, and if atoms were made of jelly, then the alpha particles should pass right through and never get to the detector. Actually, about once every 20 or 30 minutes, you get an alpha particle.
The radiation goes, hits the foil, but then bounces back and goes into the detector.
Implying that there was hard cores, and therefore that the atom was really a solar system of something hard and something going around it, as opposed to being spread out like a jelly.
Once this experiment was done, and really Rutherford interpreted it, we knew what the atom was. It was the first time we knew what the atom was.
Though his discovery was gigantic, Rutherford used a relatively simple machine to look into the atomic structure.
But we want to see what lies beyond that. For example, dark matter. Amazingly, we may finally get a glimpse of that invisible stuff at the LHC. How? By using an experiment like this.
Welcome to Atlas.
If the LHC is the world's largest microscope, Atlas is the world's most enormous lens, conceived to focus on the smallest particles in the universe. Its huge detectors are designed to examine nearly every kind of subatomic particle known to science, and some that are as yet unknown.
Atlas sits at the southernmost part of the ring. And like the other CERN experiments, we hope it'll unveil the underlying nature of everything.
Atlas is a collider detector. It's a big instrument which is used to detect the products of a high-energy collision between two protons.
Fabiola is amazing. She's devoted the last 15 years of her life to the Atlas experiment, where her greatest hope is to find the key to, among other things, dark matter.
We do have some pretty good theories that might account for dark matter, and we can test those with this machine.
Now you have to imagine that these detectors are like a kind of giant digital camera, which take pictures, and they have a very high resolution, and then you are able to reconstruct the details of the picture and then interpret it.
Those pictures are taken by multiple layers of highly sophisticated particle detectors. Every particle collision at Atlas creates hundreds of additional particles that travel through the detector. The analysis of each particle's path and lifetime tells us what that first nanosecond looked like. And one of those particles holds special interest to Fabiola.
There is one called neutralino, which has all the right features to match our present understanding of dark matter.
The theory there is that the universe has lots of these particles that could account for dark matter.
But it takes an amazing amount of technology to see them.
Components of the detectors are made of different materials, which span from silicon, pixel, as small as 40 micron, a micron is 1 millionth of a meter, to very big coils, which are 25 meter long and weight 100 tons.
The experiment is an engineering marvel.
Here's just some of the massive services that you've got. I mean, it may look a mess, but in actual fact, every cable and pipe is numbered, and we know its routing. It's a big database, but you have to. Because if you want to track a faulty cable or something like that, you need to know where it is. And obviously, when you get to the other end, which may be 100 meters away, you want to know where it's got to go to.
The Atlas detectors are capable of recording all of the 600 million collision events per second. Now, if all that data was saved, it would fill up every hard drive on the planet in one day. So a sophisticated trigger system was created to analyze and save in real time 100 of the highest quality collision events out of the millions that happen every second of every minute, of every hour, of every day.
That means that every single month, the LHC will produce and analyze about 1.5 million billion collisions. That's a number we call really big.
It's one of those boggling physics numbers, similar to the relative size of a grain of sand.
Take a grain of sand, a single grain of sand. That single grain of sand has 20 billion molecules in it. Each molecule has 90 particles in it, electrons, neutrons, and protons. If you count all the particles in a single grain of sand, it's the same number, roughly, as all the sand in the Sahara Desert down 10 feet. So that's a lot of particles.
So compared to a proton, a grain of sand is really big. Colliding two particles as small as protons is more difficult than colliding two bullets shot from the Earth and the Moon. So in order to create all those collisions at the LHC, they have to use, well, a lot of protons.
The beam is made up of 2,808 bunches, contains 100 billion particles, each of those.
Those bunches are lined up every 25 billionths of a second. That makes 280 trillion particles traveling around the LHC at once. So that's a big number.
The awesome numbers at the LHC are largely possible due to the invention of a much more humble particle collider, ADA.
So this is ADA, which means Anello di Accumulazione.
The ring for accumulation.
So this is really the first machine of this type.
ADA is more than 4,000 times smaller than the LHC.
ADA was conceived in 1960 and was realized in less than 1 year.
ADA never discovered new particles. But this great leap in physics and technology showed that magnets could move particles in a circle for a long period of time, allowing for the possibility of collisions.
It's really the tiny father of all colliders, including the LHC.
Here at CERN, the home of the LHC itself, world-class physicists from around the globe are collaborating on a revolutionary experiment. Of course, it's not the first time in history that's happened. In 1941, physicist J. Robert Oppenheimer and some of the world's smartest scientists began an experiment called the Manhattan Project.
Now, all the scientists had to not talk about what they do, which is normally not the way how science works.
4 years behind closed doors later, they had created and tested the atomic bomb.
Shortly after that, CERN was created, redeeming the name of science.
12 countries created here in Geneva the CERN laboratory.
CERN is not the Manhattan Project.
Lots of people come and say, I don't suppose we can take pictures, and the answer is yes, take as many pictures as you like. There is nothing secret here.
And the LHC is not a bomb.
It's not going to blow people up.
CERN is a laboratory that exists to do fundamental research. We are expressly forbidden to do anything else.
After 30 years of open-door science, CERN took a huge step. In 1983, they began excavating the tunnel for a gigantic particle accelerator. That same tunnel would become home to what is now the LHC, the collider they could only imagine 25 years before. And now, the LHC will begin colliding particles at energies never before reached. By a machine, that is.
By replicating the instant after the Big Bang, there are many that believe we will somehow see proof of another astonishing possibility. Extra dimensions of the universe, beyond the three we can see.
Real physical extra dimensions of space.
Explain that one, David.
What is extra dimensions? Oh my God. There's this, and there's this. 3D, you know, things are in 3D.
We think of X, Y, and Z, so 3 dimensions of space, and then time.
An extra dimension would be another direction that's, you know, at a right angle to those 3. But you can't imagine that.
Though it's nearly impossible to visualize extra dimensions, just remember that a microbe inside a piece of paper could never visualize a universe beyond that 2D piece of paper.
By definition, it has to be very small because we don't observe it in day-to-day life. In other words, we don't live in that 5th, 6th, or 7th dimension.
How do you look at something small? How do you see something small?
Sometimes you have to look big to see something very small.
So stack a few universes together, or really overlap them, and what you have is extra dimensions. The bigger question is how and where would we find signs of extra dimensions?
The 2 protons collide, and now they have so much energy compared to collisions we have been studying before, that they go over threshold, and they go indeed in a regime where these extra dimensions can be visualized.
Albert works directly across the ring from Atlas. His detector experiment is called CMS. Its name stands for Compact Muon Solenoid. But don't let the name fool you, it's not compact at all.
It's a 15-meter high experiment, and it's about 24 meters long, so it's not small. Welcome to CMS.
The heart of CMS is the single largest and most powerful superconducting magnet ever built. If all the energy was released from the magnet at once, it would be enough to melt 20 tons of gold instantly.
This experiment which you see here is actually a modular experiment. It comes in 15 different modules, and they were actually constructed on surface before they were lowered down in the hole here.
The largest of these modules weighs well over 2,000 tons and is filled with more iron than the Eiffel Tower.
Like Fabiola and Atlas, Albert and CMS will be looking hard to the detectors for signs of dark matter and other discoveries, including extra dimensions.
And we have a number of special signatures which we know of, special events which we're going to look at or going to search for.
For example, if two quarks collide and produce a gluon and a graviton, a particle that escapes from the detector, we may have hit the jackpot.
So what we will see then is an enormous large jet going in one direction, and there is nothing to compensate that jet, so there will be sort of a large missing part in that event.
So what might look like this typical example of a particle collision at CERN would be missing an expected spray of particles, or jets, meaning that the particles may have literally escaped into extra dimensions.
Extra dimensions are just cool.
I wouldn't think of it as a different kind of life form would live in there, because I think we're talking about something very small, 10 to the minus 15, 10 to the minus 20 meters, kind of small, not something that, you know, that you would bounce a ball in or something like that.
But what would all this mean to me?
What would it mean to you if we found extra dimensions? How would I know? I don't know what it means. I don't even know what it would mean to me.
It's much more than just an intellectual theory, because if we find it, it really does exist.
And the fact that that's not science fiction, that that's a part of the physical world is astounding.
All of the experiments at the LHC, CMS, Atlas, ALICE, and LHCb will be looking for a myriad of theories, like extra dimensions, by using completely different technologies.
That gives you confidence in your result.
One thing they have in common is the enormous amount of data they have to deal with.
We will have about 10,000 CPUs to analyze LHC data here at CERN. There will be a number of very large computer centers around the world,
which are all going to be connected on what is called a computing grid.
And with this computing grid, it will be like having a single computer with more than 100,000 processors.
It boggles my mind.
So what does the rest of the world get out of all this?
Aside from the myriad of scientific breakthroughs that have occurred at CERN over the years, there have also been quite a few unexpected benefits that have been born there as well.
The World Wide Web was invented at CERN, as you know.
In the first stages of creating this computing grid, the IT department at CERN developed a method for using the existing internet structure to post information to physicists around the world. CERN had what they needed, so they gave away the infrastructure, calling it the World Wide Web.
Yeah, fine. The web came from the LHC.
And you use it every single day, as well as other physics-generated toys.
And quantum mechanics, of course, is why you get these cell phones and radio and all these bourgeois comforts we wouldn't live without anymore.
I'll have to take it, excuse me.
It's science who develops the ideas, and sometimes we can even manage to make it useful for others.
The fact that the World Wide Web is something that is a spin-off of what they're actually trying to do gives you a sense of the intensity that people have in attempting to answer these questions.
And that same intensity may have led us to the verge of finding the God particle.
So why do we keep trying so hard to collide particles together? For one reason, we know there's something missing. Something we should have been able to see long ago. So we keep at it.
When two particles collide, how do you create new particles?
There should be a particle that explains why stuff has mass, why we exist.
Some call it the God particle. It's known as the Higgs boson, and though its existence was predicted in the 1960s, no one has yet to see it. To understand why it has to be there, you need to understand this.
What particle physics really is quantum field theory.
Not so long ago, it was thought that everything that exists now, all particles, existed from the moment time began. Not true.
It's the fields that exist. Particles annihilate and get created. So the things that exist now maybe were created by particles in the early universe, but they certainly didn't exist in the early universe.
Take, for example, an electron.
The electron field permeates the universe, and an electron is a vibration of that field. You have to imagine it like the surface of a lake, and you throw a pebble in, and you get some waves. Now imagine the waves kind of stay around where they are. They don't spread out. That little wave thing is an electron. Every time you throw a pebble in, you get another electron. There is a lake for every type of particle. The constant is energy. E equals mc squared says that the energy then is equal to the energy now. Could be in the form of mass, or it could be in the form of things moving around. And that's it. Quantum field theory. Fields fill space, and fields are the existence of particles.
Physicists know that there is a field responsible for mass. Therefore,
today we think that masses are generated because there is a Higgs particle.
As the universe cooled, the Higgs field condensed, making it more difficult to move through space due to what we interpret as mass.
And the God particle is the search for this Higgs particle, a way in which we can give mass to particles.
As particles move through space, their interaction with the Higgs field is proportional to their mass.
And one of the goals of the LHC is to finally find these things.
To find the Higgs would answer a whole bunch of questions, but to not find it would have even more impact.
Well, most physicists are a little uncomfortable with the fact that we haven't seen any so far.
If there is no Higgs, who is generating the mass? Would be a great mystery.
Why? Because it's the best possible explanation we have for why we exist the way we do. So how will they find the Higgs? Particle signatures.
Signatures of new physics.
This is a cloud chamber, where the naked eye can actually see traces or signatures of fundamental particles. Originally built for examining clouds, this relatively simple box filled with dry ice and gas allows us to visualize subatomic particles. Amazing.
When an ionizing particle goes through the cloud chamber, it again has only single atoms that are ionized, and you don't see those. But the mist inside the cloud chamber condenses on them, which you can then photograph, because it gets big enough to photograph.
Signatures. Tangible proof that they exist. There's an electron. Look, that's a photon.
Like the cloud chamber, spotting the Higgs particle will be a process of looking at signatures left behind by other particles in the LHC, or maybe even somewhere else. This is the Tevatron. It's also just outside Geneva, Illinois. At 1/4 the size of the LHC, it is the largest, most powerful collider presently in operation.
So we're in the Tevatron tunnel, a 4-mile-long ring, the final stage of the accelerator at Fermilab.
The Tevatron was critical to the development of the superconducting magnets that would later become the backbone of the LHC.
Tevatron is like time machine because it can produce particles at the beginning of the universe.
The physicists here have been searching for the Higgs particle for 25 years. And some say they may find it before the LHC turns on.
Will they find the interesting Higgs particle before LHC is on? They have a tiny chance.
But once the LHC turns on, the primary attention of all physics, including that of the Tevatron, will be at the LHC.
This room is called Remote Operation Center. So that this is where we can monitor what's happening the other side of the globe at CERN.
A remote operation center across the globe to look for the God particle. Sir Isaac Newton would be pleased.
Isaac Newton was arguably the greatest physicist who ever lived. Imagine a time before modern science when there's a guy who could predict things about nature. This looks like magic to the average person. It was really the birth of what we call all of science. It was proposing something, and not just qualitatively, but quantitatively predicting a result.
In terms of our detector, Newton's laws has a huge effect, right? We have to actually build a detector that's structurally sound and stands up to gravity.
Newtonian way of thought, approaching the world with a question. Why does this work? I don't know, and I'm not going to assume I know. I'm going to try to answer the question and test to see if my answer is correct. That way of discovering the world is how we live today.
It's a Newtonian world, but it's also a quantum mechanical world.
It is, in fact, a quantum mechanical world, and it has been since that first nanosecond in history.
Quantum mechanics describes the laws that govern the physics of subatomic particles, how they behave. At the quantum level, Newton's laws break down. In our experience, objects obey very strict physical laws of motion and velocity. But in the quantum realm, a particle cannot be said to be in any particular place until it is actually observed. The best we can do is assign it a probability of being at any given point at any given time. Therefore, every particle has a chance of being anywhere at any time, or everywhere at the same time.
Pretty complicated, even for some of the smartest people on the planet. In fact, one scientist completely abandoned quantum mechanics after contributing to its inception. Perhaps you've heard of him.
You want me to say something about my theories?
Einstein is really special because he really did everything by himself on a problem which other people were even scared to try to attack.
We all work with Dr. Einstein.
He's my good friend in a sense because the accelerators would not work without Einstein. In fact, I experience Einstein every day. It's become so natural that I'm not even shocked anymore by these concepts.
At the end of the 19th century, the physics community thought it had basically figured it all out.
We understood gravity, we understood light, electromagnetism. It was almost all complete. There's just a few calculations left to do. And then Einstein throws a huge wrench into it and gives us relativity, says things move through time differently if they're moving relative to each other.
And of course, he gave us arguably the most famous equation ever written, which basically states the amazing truth that energy and mass are different forms of the same thing.
There are a number of ways you can use Einstein's equation, E equals mc squared. One of them is you can build a power station, you take a tiny bit of m, mass, and you get the energy out of it, and you power a city. What we're doing is doing that process in reverse.
He came up with some of the most dramatic developments in physical theory in 300 years. He created the birth of quantum mechanics. And then, of course, he would make teenage girls faint. I can't explain that, but he was bigger than Elvis. And he was a very good-looking man as well.
Some people have fears that the LHC might produce something dangerous.
We're going to create black holes that are going to destroy the universe.
Or maybe the LHC could be used as a weapon or something.
No, we're not building a bomb here.
There is no sort of weapons building.
It requires 17 miles of real estate in order to actually produce a beam of that strength. Not very practical. However, it is practical in producing cutting-edge science. And the hope for the LHC is we'll see things that we've never seen before, and we'll understand things that we haven't understood until now.
Why then is this great LHC hidden in a tunnel 100 meters underneath Europe?
Well, you got to put the thing in a tunnel. The first reason to put it in a tunnel is there are cosmic rays coming from outside the Earth and bombarding your experiment. So you put it inside a tunnel so that the cosmic rays don't disrupt your beam.
So the depth keeps cosmic rays from tainting results.
But even more important, perhaps, is that when the beam is turned on, while it's going, it's emitting this radiation. And the radiation is coming out, and you need something to shield the radiation from coming out of the tunnel.
Radiation, which is why you can't be in the tunnel when it's on.
If you're in our collision hall and you're hugging the beam pipe while the collider is running, but you would die almost instantly from the radiation.
So the big question is, what actually happens to all the radiation?
When there is no particle left, there is basically no radiation left.
When you turn it off, of course, there's no radiation.
Still, the LHC is not without dangers, which is why huge care goes into keeping people and the machine safe. With hundreds of trillions of protons traveling at that kind of energy, one situation is particularly worrisome for scientists at CERN. A disaster called a quench.
When you're steering these protons that are going that fast around and around in a circle, you're doing that using very high magnetic fields. And the way that we generate those magnetic fields is with an electric current flowing in a wire.
12,000 amps of electrical current. Now, considering your entire house only uses about 100 amps, the LHC's whopping 12,000 amps must run through superconducting cable. And to make a cable superconducting takes a lot of work.
It's a very low temperature phenomenon.
The cable has to be kept extremely cold, about as cold as the dark side of Pluto.
In order to get those kinds of very low temperatures, about 260 degrees below zero, we use liquid helium.
Which is dangerous in itself. You can't touch this stuff.
Because it's so cold that it will be completely frozen.
If the temperature of the liquid helium rises even a few degrees, the results can be disastrous.
Something could happen that causes the superconducting cable to heat up to a temperature above where it superconducts, and suddenly this 12,000 amps sees a resistance, an electrical resistance. That's a quench.
Now the wire acts like any other wires, so it acts like a heater. It heats this magnet up, and now the liquid helium turns into gaseous helium.
All in a fraction of a second. So now you have to get that deadly gas the heck out of there.
And that gas has to go somewhere, otherwise the magnet will blow up.
Which you obviously want to avoid.
You have to have very sophisticated systems that monitor for quenches, see quenches coming, and when they see one coming, they dump all that current out very quickly into quench resistors.
Because if the magnet goes down, suddenly this beam, packing the force of a small aircraft carrier hitting the beach at 30 knots, is now flying out of control.
When you hear the LHC guys talk about, oh my God, there's a quench, they really have a problem in the sense that that quench could missteer the beam. And that beam, if it's missteered, will now go right into the side of a magnet and blow a hole in the side of that magnet.
If a beam got loose, well, it would punch a hole in the wall about 100 meters deep.
If you were hit by the beam, you may wonder, what, am I going to vaporize?
No, you wouldn't vaporize. You would just die. And I think relatively quickly.
Which is another reason why there's no one in the tunnel during its operation. But it's a very real danger for the very expensive equipment.
It's something we will have to deal with, but what I can say is that every single magnet in that tunnel has been tested, quenched, put through its paces on the surface.
All of this work, all of this technology, and all of this danger to find something, and one possible something that could address everything, is called supersymmetry.
The fundamental essence of supersymmetry is that there should be a symmetry between particles and forces.
What the heck is supersymmetry? Supersymmetry, that's a toughie.
Supersymmetry is a theory where effectively every particle has its own superparticle.
For every known particle, like the electron, there's some other particle which is the partner of that particle, the superpartner.
Except that it's heavier, more massive.
We look hard enough, we should find a whole other double copy of this world where there's a force-carrying particle for every matter particle and a matter particle for every force particle.
It's a symmetry between matter and force.
This is often like to talk about supersymmetry as being a mirror.
You have a mirror, and on one side of the mirror is the real universe, and on the other side of the mirror are your supersymmetric particles.
Everyone who believes in supersymmetry believes that when we go to high enough energies, the mirror will break down and we actually will see particles and their superpartners at the same time.
The LHC may actually find supersymmetry, or for that matter, extra dimensions, dark matter, or the God particle.
All of these theories are there to try to explain what's happening at this fundamental temperature, at this fundamental energy, which seems to be an underlying part of particle physics.
But they could also find something else.
The LHC could find something we didn't even think of.
Which could be the greatest discovery of all. And that leads to the final question. We understand what we're looking for, how it works, where it is, who was involved. But we have yet to understand why.
Why?
Why?
Pourquoi?
Why?
Why?
Why go to such great lengths just to witness the momentary production of these historic particles?
Gonna have to.
Nature has just an infinitude of phenomena that it hands us, and we just are there to discover it.
I want to find truth.
That's why I'm here.
There are more open unknowns ahead of us.
This is a truth.
Nature itself has zillions of surprises for you.
We're about to open a new door.
It's truth.
That's why we like science.
There's something behind what's happening, and I want to know what that is.
The LHC is a doorway And when we open it, we're going to find some answers. I don't know what.
Whatever it is,